Okay, hello. I am going to start sort of in an unusual manner. Instead of giving a long introduction to the topic as we would do normally in lecture one, I figured it would be most appropriate for me to make that discussion in more detail in class when I come back. And so I'm going to do a relatively quick movement from zero to something so that we can then focus on some specific developments that, something quantitative that you can work on, so you're not just kind of hanging out waiting. As I mentioned in the email that I sent, I am actually this week in Chile in the World Conference on Earthquake Engineering, presenting some work on damping. And I'll be back on Friday. And so we will meet regular time, regular location on Monday, and then at that time we can talk about, whether we would like to, if you guys are interested in modifying, where we meet, how long, when, where, and so on. And I'll tell you what the whole plan is. At this point, the number of students that are in the class is small enough that I have a hope that I will be able to work with you guys in this case so that perhaps we can actually come out with a couple of papers, so that perhaps each one of you, or maybe in duos or something, can write a paper that we can submit at the end of the class. Depending on how well the paper comes out, we might choose a conference on structural health monitoring that takes place every year, or who knows, we might get ambitious and even think journal type of publication. I've got some very concrete ideas, but I'm going to do that when I come back. Okay, so let me start right away with the idea of system identification as a short introduction. So this, I was making this box here so that the camera can focus. Let me take the box out and using this towel because this thing seems to get very dirty right away. So let's say that we have a generic system, which is this blob here, that I shall call capital omega. Now that system, in our case, because we are, I assume, in structural engineering, it's typically a structure. But in a more generical sense, this is just a system, okay? It could be a plant that actually produces, some chemical. Or it could be an airplane, or it could be anything. It's just some system. Now that system, which we don't attempt to describe right now, could be subjected to some inputs that we will call U, right? And when we use the letter U here, we mean inputs that somehow we know what they are. So these inputs are measurable or deterministic or known. But the system could also be subjected to some additional inputs, which we shall call omega. Okay? Let's say this is a function of time, and this is a function of time. And these omegas are also inputs. They're just as inputs as these are, but what distinguishes them from U is that we have no way to measure them. They're just there. Okay? For example, if this was a structure, this input may be, for example, let's say a recorded earthquake. And this W could be the wind that at the same time was acting. So maybe we recorded the earthquake, but we don't have the wind that was acting at the same time. Okay? In any case, this system has a response, right? Now that response is, let's say, X as a function of time. Now X is a collection of variables that for the time being we're just going to call them the state. Okay? So X is the state. And by that we mean a collection of variables that is sufficient to describe what we are interested in, or anything that we could be interested in on the system omega. There is a measurement xt. Now, there is also some, let's see, there is some measurement box, which I'm going to call it M. And out of that measurement box comes outputs. And so outputs are things that we can measure. So if in this structure I put some sensors, what I measure is YT, right? Actually, let me be a little bit more precise. Wait a second. Out of this measurement box, okay, there is a Y, I'm going to call it Y bar, which would be what I would be able to measure if I had a perfect sensor. But in reality, I don't have perfect sensors, because whenever you try to measure anything, you measure the thing plus noise. Or in fact, what we mean by measurement is what? I mean, we create some device, we put the device gives some voltage, the voltage gets interpreted and so on. So we don't really get to see the actual quantity. What we get to see is a perturbed version of that quantity, which I should call Y, right? And nu here is noise, right? So nu is noise. Now, in your normal training in structural engineering or in civil engineering, our objective is usually something like this. We know what the input is. It could be statics, but let's say in dynamics. We know what the input is, and we know what the system is. Or at least if it's in design, we're trying to figure out what we would like the system to be. But basically, we know the input, we know the system, and our objective is to find the response. That's a structural dynamics problem. So it's a forward problem. From the input, we know the system, we calculate the response. Now, in system identification, our objective is actually to learn something about the system, given the fact that we can measure the input and the output. So let's say that the forward problem, okay, the forward problem, which is the problem that it's more common, at least up to this point in your view, in your training, would be given U of t and the system, get x of t, right? So the forward problem is given ut and the system, and by the system I'm talking in generical terms, right? I'm not saying anything. You just think in this in abstract terms. In practice, if it was a static problem, the system might be the stiffness matrix. If it's a dynamic, it could be the mass, damping, and stiffness matrix, but you just think about the system. So given the input and the system, you want to compute xt. That's the forward problem, the standard one. Now, the identification problem, is, at least one version here, would be given u of t and y of t, get some useful information about omega. I will just say get omega right now, which is going to be a little bit too ambitious because we might not be able to really get a full description of omega, but that's, you get the point. So we are trying to say, given input and output, what is the system, instead of giving input and the system, what is the output. Now, in system identification, there is one sharp distinction with the standard way to think of design or the forward problem. It is that this problem only makes sense, right? The identification problem only makes sense when we're talking about an existing structure, an existing system, let's say. There must be some system that exists in order for us to ask an identification question. Otherwise, there's nothing to identify. And more importantly, actually to be more precise, the system must exist. It cannot be blueprints like we do when we design a bridge or a building, right? That we just have blueprints. If we're doing system identification, there is some system that exists. In addition, for the system existing, there must be measurements. Measurements must be available, otherwise there's nothing to say, right? So you can then say that system identification is, in a generic expression, way to state it, is in system identification we attempt to formulate models for systems, not from the basics of the physics of the system, but on the basis of the observations of how the system responds to certain inputs. Okay? So at the end of the day, we want to know something about this based on this and this. Now, sometimes we actually don't know U at all, or there may be no U, and we only have that the structure is being excited by loads that we cannot measure. That's possible, and we can still do something, right? A typical case might be a situation of a bridge that we want to learn something about the bridge, about the properties or something like that, and all we have is just the vibrations of the bridge when the traffic is going through, but we really cannot measure what is the excitation. We know it's the traffic going through and some wind and things like that, but we don't have this U as a function of time. We can still learn something, right? Now, so this is a very generic description, and the important thing here, well, many important things, but is to keep in mind that this right here, omega t, is what we call unmeasured disturbances. Okay? WT are unmeasured disturbances, and VT is measurement noise. Both of these things will be with us all the time when we're doing system identification. Okay? XT is the state. We have unmeasured disturbances, we have measured inputs, and we have the output. This right here sometimes is called C. Well, no, that's not true. That's not true. This is the measurement box. Let's just leave it like that. This is a plus. So we're just simply adding noise and we get this. Okay? Let me see. Okay, so let me erase this part. Or let me see here. I have some notes here. Right, so let's say a little bit about what we can do with this information, or why we would want to ever do some system identification. And let's look at it in the context of some practical problems. So, uses of System identification, SID, right? What we might want to use it for? Well, we might want to use it, one, for model improvement. Okay, model updating. It's called model, in the literature we refer to it as model updating. So let's take one particular example. First, from non-civil engineering and then from civil engineering, I guess. Let's say that you are designing a car. Okay? So it's the new version of the whatever, you know, car coming out next year or whatever. So what do? Well, the design engineer is interested in making the car ride as smooth as possible, etc. Right? So you go in and you make a finite element model of the car, right? And now you have your finite element model of the car and so on. And so the finite element model of the car allows you to ask some questions. You can do dynamics and say, and you can look at the aerodynamics and you can say, okay, what kind of vibration levels will I get if I, you know, make the mirror like this or like that and so on. So you can use the finite element to improve your design and blah, etc., right? But then what happens is that you are now at a certain stage and you build a prototype. So you build one, right? Now the finite element model would say, for example, now we haven't done dynamics here yet, but let's say the finite element model says that the first frequency of this car happens to be, I don't know, 22 hertz, right? And it has a certain shape, and let's say that the second frequency of vibration is 39 hertz, and I don't know, here it goes like that, and let's say that the 10th frequency is 315 hertz. And then there's more, right? So anyway, these are finite element predictions. You made a model. This is what the model says are the natural frequencies of your prototype, of your car, of the car that you're designing. You plan to build many of them, right? But now you build this prototype and you appeal to system identification. That is, you put some sensors on the car, right? You put a sensor here and a sensor here and a sensor there. Okay? And you excite the car, maybe you hit it with a hammer or you excite it with a shaker or something, and you take measurements, right? And from those measurements, and what we will learn on system identification, then you find that the frequency of the first mode was not really 22 hertz, it was 25.7 hertz. And the frequency of the second mode was not 39 hertz, was actually 38.7 hertz. And the frequency of the third mode was not 315, but 331 hertz, etc. Right? In other words, you are never going to make a model that is exactly correct, right? Because reality is just simply more complicated than any model. So you've done your best. This is what your finite element says. But now you go to System ID and the identification tells you these are the actual frequencies. Now obviously the predictions that you make about how smooth your car is going to ride and so on are based on this model. And they're only as good as the model is. So what you'd like to do is you'd like to improve the model. In other words, you'd like to update the model. How? By using information that you were able to extract from the car itself. So by doing system identification and knowing that these are the frequencies, then you could come to your finite element model, right? And you could tune it. That's obviously an art in itself, but you want to tune the model. So you take the model and you say, I need to change, you know, I wasn't too sure about the stiffness of this connection, and I wasn't too sure about the model of this bearing, and I wasn't too sure. So you start modifying it, right? And as you modify the finite element model here and there, your task, of course, is to make these numbers come as close as possible, right? All the numbers that you're able to identify with the finite element model, with system identification, you want to make the actual model match them best you can. So, okay, so that is in a mechanical thing like that, right? Now you might also have the situation true sometimes in, I can give you an example, in the civil engineering realm. You might have, for example, an existing building, right? You have an existing building. There was an earthquake and so on. The building is like this and like that. The owner is concerned, there hasn't been an earthquake. Let's say the owner of the building is concerned about how this building will perform, or something like this. So your company is hired. You are asked to do some structural analysis and some predictions as to behavior and so on. So you make a model of the building, right? Again, you are uncertain about many things. For example, you're not certain about whether these connections are rigid or not because it's steel. You're not too sure about the foundation flexibility, whether you should include the soil or not. You're not certain about many things. But you are able to go here and to put a sensor, and here and to put another sensor, and maybe you can observe the vibrations that take place during the day from the ambient sources. That is, you don't need to even get permission from the owner to hit the building or to shake it. You just sort of observe these signals. Because we have accelerometers, they're accurate enough, sensitive enough, that just from the traffic of the cars passing by, right, we can get enough vibration in here to be able to measure it. And then we take these measurements and we do system ID. And from that system identification, again, I'm keeping it very fundamental right now, but let's say that we find that the first frequency is, 6 radians per second. Then we had a finite element model, right? And in our finite element model, the first frequency of the model, may have been, 5.1 radians per second. So what do we conclude? Well, our model is not that great. We are missing the resonance, which actually in reality on this building is at 6 radians per second. Our model is saying that it's at 5.1. So what do? We go to our model and we try to see who do we think is responsible for the fact that our model is not matching reality, right? And again, that's an art, and that will involve a lot of stuff, and we'll have time to talk about it in more detail. But maybe I come to the conclusion that, I was modeling, that the structure happens to be stiffer than my model, right? My model is 5.1 radians per second, and this is 6 radians per second, it's more, so it's faster. And therefore, then I'm thinking, oh, you know what? What's happening is that there are some light partitions, but these partitions that are in here, these sheetrock partitions are adding some stiffness on this building, and I think that they are the ones that are responsible for this change. So I'll see if I can do something to modify my model to account for the stiffness of those partitions. Maybe it's something else. Maybe it's the opposite. Maybe this, instead of being 5.1, was what did I say? Let's see if I'm doing this backwards. Let's see, what did I say here? 2 pi over omega. Well, let me put it in period, which might be simpler. So t, let's say that the t of the model was 1 second, just so I don't get messed up here, let's try this, and let's say that the t, this is the t of the model, and the t in reality was 1.3 seconds. Okay, that's easier to visualize. So if I have a model and the model says it's 1 second, and the reality is saying that the period is really not 1 but 1.3, then in this case I would say my real structure is softer, right? The real structure is softer than this. It's vibrating, it takes it more time to go through a cycle than the model. So maybe what's happening is that instead of the, and maybe I detect that the problem is that I must somehow account for the softness of the footings, right? That there is some flexibility here at the foundation level and that I need to include it. And so I have maybe a spring constant here at the foundation level, and I play around with the spring constant until I make this thing be 1.3 seconds. And then I say, okay, well, that's a better representation. Now, that may or may not be true, right? I should not fool myself, because maybe that's not the reason. Maybe there's other reasons, but again, that would take us to another domain. But you get my drift. My point here is that we have some information about the reality and we want to adjust the model in that direction. So that's one possibility, is model updating, why we might want to use system identification. Another reason is for structural health monitoring. So structural health monitoring is another reason. So in structural health monitoring, I might have a structure, right? And I'm interested on putting some sensors, and I'm interested to know if anything doesn't look right. Now, how can I do that? Well, with system identification, I may use the measurements that I have from my sensors, right? Now, looking at the sensor data directly is not very useful, right? Because every day I look at it and it just looks like a mess, right? A bunch of numbers, a gazillion things. I plot them. How am I going to know something's the matter? I don't. But what I can do is do system ID, let's say every day at noon, or at 3 p.m., or twice a day, or whatever, and I find that this bridge, in its healthy state, I don't know, has the following, I'm using in these descriptions now only frequencies and periods, right? So has the following period, right? So the first mode is 2.7 seconds, this is 1.3 seconds, this is 0.9 seconds, let's say. Now, of course, these values are not exactly like that, because it depends on whether it is cold or warm, or whether humidity is high or low. So this 2.7 is really a mean of some distribution that we find, right? And this 1.3 is also some sort of a mean of some distribution that we find from measuring this thing in many days and so on. But anyway, we know that when our bridge is healthy, these periods are like this, right? Now, on one day, we find that this period proves out to be 3.1 seconds, for example. Then we're really worried, so we stop the traffic. Why is the period that is 2.7 normally, right? Why has it gone to 3.1 seconds? And then we might go in and find out that the connection of this cable to the bridge over here somehow has been fractured, or, I mean, I'm making stuff up, right? But the point is that this cable is no longer working quite as it should be, and the deck became just so much more flexible, and the period went up, right? That could be. So I can use the measurements to perform identification constantly, and from the results of the identification we can infer that you know, something's the matter. So in the case that we use structural health monitoring, the system identification can be viewed as a way to compress the data, right? We want to compress the data into something that it's easily manageable and that can give us clear information on what we're interested in. we can also well, actually, also within the context of structural health monitoring, I should say, because we are going to say quite a bit on this, in the context of structural health monitoring, we can use system identification right, as a way to compress the data. So we don't look at the signals directly, right? But it's interesting to note also that in structural health monitoring, we might think in terms of detection. So the question of detection is simply to say, is the system okay? Are you sure? You reasonably sure? Or you're pretty sure that something is the matter? That would be a detection question, right? You might say, I think something happened. And if you think something is the matter, you may want to ask us the following question, which is, what? Or more precisely, where is the problem? Right? We refer to this as location. So the second stage in a structural health monitoring issue is to use detection, and we might want to know something about where the thing is located. Now, in this case, we want to continue to take advantage of our ability to do system identification. So hopefully, we would like to be able to say something about the location from looking at how the system identification has changed. Okay, and we will be taking a look at that. And finally, we might be interested on how large. So not only do we have a problem that has been detected and the identification allowed me to do that, not only does the identification also help me to pinpoint where the problem is, or at least the general area of the structure where the problem is located, but I also might even want to use system identification results also to say something about how large is the problem. Is it a question of a little bit of reduction of a stiffness somewhere, or is it a large case? And this term, which is usually the one that's least well developed, is the prognosis, which is really the question of what happens if I don't do anything right now. Is this a question that I need to take care of right away, or do I need to intervene or not? We should always keep in mind that analysis, the structure doesn't know how much we analyze it or how much identification we do, right? The structure only knows what you do to it. So system ID, structural health monitoring, all these things, one has to keep in the back of our minds always constantly that all we're doing is providing information to people that must make decisions with regards to interventions. Because all that matters in the end, you know, structural health monitoring, system identification does not provide safety per se. It does not provide more reliability per se. It only provides information that, if appropriately used by someone that is able to make an intervention, then would increase the safety or the reliability of the structure. Okay? Now, in certain instances, we might also use system identification, not necessarily because we are trying to find damage, not necessarily because we are trying to improve a model of a particular structure or something like that, but there are many other settings. And let's say I am now, this week, as I said, the reason why I'm taping this, I'm in Chile presenting some work, right? Now, this work has to do, in part, with what are the values of damping that should be used in designing structures, let's say buildings, concrete buildings, steel buildings, and so on. What value of damping should be used? Well, this is not something that we can find from studying blueprints, because the damping mechanism is not understood at that level. But what we can do, of course, is to perform system identification. So if we have buildings that have been subjected to earthquakes, right? So here is this earthquake, and we measured how the building moved, system identification allows me to find that this building had a damping ratio, let's say, on the first mode of 5.2%, right? And it turns out that we have been measuring the response of buildings for many years now, right? More than 50 years. And we have lots of data. So part of what we're reporting is we can do system identification with this very large data set and obtain all these dampings of real buildings that were obtained from the analysis, right? And then we can say, well, look, by looking at buildings that are made of concrete, we find that, I don't know, you can make it as particular as you want. You could even say buildings made of concrete which are between 10 and 15 stories, if you think that height is an issue. Or you can say whatever. The point is not to describe the research, but the point is that you could say that we recommend this number, 3.7% damping, or this formula, or something. The point here is that system ID is the key, because it's with system identification that you've been able to convert the measurement of the sensors to the quantities that you're interested in. Okay? And then that number that you come up, or that formula, will be useful in the future for those people designing concrete buildings or for designing steel structures. Okay, so as I said, I was going to keep the discussion in the intro to not very long. So I'm going to begin right away now, moving into a description of what is known as the state space model of physical systems. Okay? Again, let me say one more time, what is the state? In order to predict the future of any physical system, it's obvious that we need to know, so if I have a system at time t, and I want to say where is this system, or what's happening to it at time t1, right? Then how the system changes from t to t1, and the system, I don't mean the properties of the system, I mean how the response, if you want to think in terms specific, you could say, since we are structural engineers, you can think about this three-story building. This three-story building at time t was, let's say, at this position. I want to know where this three-story building is a little bit later. It's at this other position, right? From t to t1. So in order for us to predict how something changes from one time to another, we need to know, obviously, the excitation that takes place between the two times that we're interested in, because it's obvious that whether this building goes from here to here depends quite a bit on what are the forces that are acting on it between this time and this time. That's clear. It depends on the excitation. But in addition to the excitation, it depends on where the building was at this time. And the description of the structure at any given time is what we refer to as the state. Okay? So the state, to say it in precise, is the state is the collection of variables needed to predict the evolution in time if the excitations are known. The evolution in time of the system. And I'm being a little bit redundant here because I'm using system in a loose manner. But the state is the collection of variables needed to predict the evolution in time of the system, globally speaking, if the excitations are known. So now, if I tell you that I have this system, to be precise, right? If I have this system, this building, 3 stories, at time t equal to 0, and I want to know what's going on in this system at time t equal to 2 seconds. And I happen to know that between t equal to 0 and t equal to 2 seconds, what there is a load of 100 kips that acts at the roof, and that's it, right? Let's say I have a load that appears here, acts at the roof like that for 2 seconds. I want to know where the building is here. I know all the properties of the building. What do I need to know at time t? Well, I need to know where the system is at time t in order to do this, because the load is going to produce changes, but I need to know what the initial conditions. So in a model like this, if we make a model in the simplest sense of having 3 degrees of freedom, as we normally would be for something like this, right? Horizontal motion, so degree of freedom 1, degree of freedom 2, degree of freedom 3. Is it sufficient to know delta 1, delta 2, and delta 3 at time t equal to 0? Is it sufficient to know the displacements? The answer is no. You need to know also the velocities, because knowing that the displacements could all be 0, right? That doesn't mean that the velocities are 0. I could have non-zero velocities at these points, and that's going to affect what happens. So it turns out that the state of a system, of a linear structure that we're looking at here, is really the collection of degrees of freedom and the derivatives of the degrees of freedom. So if we think about a structure having n degrees of freedom, the state is 2n. Okay? So it's not only the displacements, but also the velocities. Another way to say it is this, as a last one. If I know that this ball is in the air at time t, what do I need to know where it is at t0, what it is at t1? Well, I need to know where it is, which is that it's here, and I need to know its velocity, right? So if I happen to know that its velocity is v0 in that direction, then I can find out where it's going to be at t1, right? It's going to be here. So it was not sufficient to know where the ball was at time t0. I also had to know what the velocity of the ball at time t0 was. All right? Now, what we're going to do is to start with linear time invariant systems, linear time invariant, which can be described by the second order equations mq double dot plus cq dot plus kq is equal to b2 ft. Those who have taken the structural dynamics with me, this will be obvious. If you haven't, it doesn't matter. I will describe it in a second. Mass m, c, and k are matrices that are n by n, right? This is known as the mass matrix. This is known as the damping matrix. This is known as the stiffness matrix. At this point, even if you know nothing about this, it doesn't really matter, right? You can still follow that some system, and in fact all linear structures can be described this way, that are, well, I shouldn't say all linear structures, but a large subset of structures can be described, the dynamic equilibrium can be described by this set of equations, which is second order linear differential equation set, right? Mass times accelerations, damping times velocities, stiffness times displacements equal loads. B2 is the distribution of the loads, Ft. Right? And Q, n by 1, are the degrees of freedom. Okay, so we have an n degree of freedom system, which is linear, and time invariant means that the mass, the damping, and the stiffness matrix are constant. They're not changing with time, right? And B2 is the distribution of the loads. So the course in structural dynamics, we attempt to find out first how to formulate these equations and how to solve them, okay? In system identification, we actually want to measure some of the Q's, obviously not all. That's one of the problems that a lot of times people have, is that they write papers in which you're measuring all of the Q's. Well, you know, essentially that's an academic problem. What you can do is measure some of the Q's, unless you're talking about little simple things in a classroom. But I mean, if it's a real situation, forget it. So you can measure some of the degrees of freedom, and you can measure perhaps some of these excitations, right? All right. So this is the equations. The vector B2, it's, I don't know if to stop to explain it, maybe not, I won't explain it right now. I'm assuming that you guys know it, and if you don't know it, don't worry about it, because you can then ask me when I come back, and I will describe it in detail. Right now it's sufficient just to see it mathematically as the fact that B2 is a vector that, that has n rows and r columns, and r is the number of inputs. Okay? R is the number of inputs. So it has n rows and r columns. Whoa, that's a poor way to write. I shouldn't say belongs to, B2 belongs to the reals and has n rows and r columns. Okay? Q belongs to the reals, has n rows, 1 column. M, C, and K are matrices that belong to the reals and are n by n, rows and columns. Okay? Okay, so I erase this part. Actually, I'll write the equation again just to give myself the most room. So I put the equation here again. M Q double dot plus C Q dot plus K Q is equal to B2 Ft. Okay, so that's the equation that we start. We want to transform these equations to what we call state space. Why is this not in state space? Because the state is only the displacements and the velocities. The state does not have accelerations. So without any further discussion, I think you can see that I can write the following. Q dot and Q double dot is equal, and I will open this like this, and now I will put here one derivative less, so this will be Q and this will be Q dot, right? And then I'll open this, leave it blank, and I will write F of t here, and then we will fill in the blank. Now from this equation, if we multiply by m to the minus 1, you can see that Q double dot would be equal to m to the minus 1 B2 times Ft minus m to the minus 1 c times q dot minus m to the minus 1 k q, right? So multiplying this equation times m to the minus 1 and solving for q double dot gives us that. Okay? Multiplying times m to the minus 1 and solving for q double dot gives us that. So if I come here and I write that, I can see that is m1, m to the minus 1 b2 times ft, so that goes here. M to the minus 1 times b2 times ft. I also see minus m to the minus 1 cq dot, so minus m to the minus 1 cq dot, and I see minus m to the minus 1 k, so minus m to the minus 1 k q. So this right here is that equation, right? Q double dot is minus m to the minus 1 k q minus m to the minus 1 c q dot m to the plus m to the minus 1 b2 ft. And this first thing here is simply q dot is equal to q dot, and so we've completed the process, right? Now if that's complete. That's just simply saying that plus has the identity q dot is equal to q dot. Now I can see that because this is the derivative of that, if I call x of t the collection of q of t and q dot of t, right? Then this writes, what is this here? If that's xt, then this here is simply x dot of t, right? This matrix, I can give it a name, and I will call it AC. And this is xt. This matrix will give it a name, BC, and that is ft. And this equation right here has no more information than the original, but has only one derivative, right? X dot, it's related to x. There are no two derivatives here. This is the state space formulation of the equations of motion. Okay? That's the state space formulation of the equations of motion. Now nothing comes out for free, right? This system of equations was n by n. That is, the degrees of freedom were n. But there were two derivatives. This system has only one derivative, but the system of equations is 2n by 2n. Because A, it's 2n by 2n, right? Now you can say that in the process, when we solve this system, not only do we get the displacements, when we solve for x, we get the displacements and the velocities at the same time, right? Okay? Now notice that the matrix A, C, C is intended to mean continuous time. That the matrix AC has all the properties of the system. It has the mass, it has the stiffness, and it has the damping. So all the properties of the system must be reflected somehow on the matrix A, or are reflected in the matrix A. The matrix B, which is BC, which is this one, depends on the inverse of the mass and on the distribution that the loads have, which is B2, right? And FT is, of course, the loads. And FT, I don't know if I put it before, but FT belongs to the reals, and it is equal to R by 1. That is, there are R values on FT at any given time. Okay? This is the state space formulation. Okay. Now, I will instead of making this like, you know, lecture 1 and then starting lecture 2 and so on, I'm just going to continue and cover a certain amount of time that we'll, use to be the, I don't know if all today, but in this lecture I'm not going to try to stop at beginning because there was the 60 minutes or whatever it was that we have dedicated for the time. So let me just continue. And what I want to do now is, and I want you to appreciate this, we're going to run into this equation, not only run, we're going to be dealing with this all the time. So this is the state space formulation of the linear system of equations of a linear time invariant system. X dot, X is the state. This says the derivative of the state is equal to a matrix times the state plus another matrix times the excitation. And if the excitation happens to be 0, then this simply is how a state evolves in time. X dot is AX. Okay? I'm just going to go check that the recording is taking place correctly. And as far as I can see, it is. So I come back. So we have X dot as a function of time is equal to AC times XT plus BC times F of t, right? What I want to do now is to try to solve this equation without saying anything about what Ft is and so on. Just let's see what we can do analytically. So here's what we're going to do. We're going to multiply both sides times the matrix KT. Now don't confuse K with being the stiffness matrix. This is just a matrix K, which could change with time and which belongs to the space 2n by 2n, right? So if I multiply both sides by the matrix KT, we would get this, right? Okay? Now, let's take a look at what is the derivative with respect to time of the matrix KT multiplied by the state XT. If we use the chain rule, the derivative with respect to time of that product, KT times XT, is going to be what? Is going to be XT times the derivative of XT plus plus the derivative of K, the matrix, times X, right? So that's what that will be. Now what happens is I recognize this term here, K dot T times XT is this guy. Therefore, what I want to do is I want to write this term as this minus this, okay? Therefore, replacing XT dot T by this minus that, we have that the derivative with respect to time of KT times XT minus KT times X dot T, right? This minus this is this, and that was that. So that's equal to the right hand side, which is KT times AC times XT plus K as a function of time times BC times FT, right? Okay, now we're going to say the following. XT is so far whatever I want, right? We haven't constrained it in any way, except that it is of the size 2n by 2n so that it can do the multiplication. So it's congruent. But other than that, xt is whatever I want. So if we can choose xt any way we like, we might as well say let's choose this to help us out. How would a choice of xt help us out, at least at this level? Well, if you look at this term and this term, no. What's going on here? I think I made an error. I made an error because I want xt, kt, x dot t. So I want this. So I have to subtract, yeah, I took the wrong one. I have to subtract x dot t xt. So my apologies. Remember, I have here xt, x dot t. I mean, k times x dot. From this derivative, what I want to do is take k times x dot, which is this. It must be this term minus this term, and this term is this term, right? Okay, so I've corrected it. Now, what I'm going to do is I recognize that this term and this term both have xt at the end. And if I choose minus xt dot to be the same as xt times ac, then what's going to happen? It's going to cancel this term with this term, right? If I choose that. Okay? But since kt is arbitrary, it seems like I should be able to do that, because this is some sort of matrix differential equation that I should be able to solve for finding kt. So that means, okay, I will solve it, I will get that xt, no longer xt is whatever I want, xt is this, but with xt equal to that, this will happen. Therefore, since that is true, I can come up here, I need space, so I need to erase this.